Hi everyone, welcome back. This is the second part of the lecture on tangent planes and linear approximation. In this part we are going to look at differentiability and differentials. The place we're going to start is with this notion of an increment. So here's the setup. We've got a function f, and we are imagining that we are at some point in the domain. Let's call it AB. We go ahead and we work out our function value at AB, and I'm imagining that that's on some surface here, the surface which is the graph of our function z equals f of x, y. So this is going to have some z value coming out, so it's going to be some value sort of right there. Just trying to draw these lines in here so we get a little bit of perspective. So that's our z value coming out, so that's our f of AB. And what I'm interested in is what happens if I change my input a little bit. So instead of being at AB, I move a little bit. I go to like an A plus delta x, and I move over to a B plus delta y. So I change a little bit. I change delta x in the x direction, and I change delta y in the y direction. So I get to some new point here. So there's my little change. Delta x and delta y, as I've drawn them here, I'm kind of thinking of them as positive, but they don't have to be. They could be negative. I could have gone back along the x-axis in the other direction. I could have gone back along the y-axis in the other direction. The idea is I've changed my input just a little bit. If I evaluate my function at that new point, I get some other value, and the question is, for this new value, what is the difference in the heights between these two values? So I'll just indicate that here. We're interested in how did our height change? What's the change in the z value between these two? And that is what we're calling the increment. That's delta z. Delta z is the change in the output. So it's the value of the function at the second point minus the value of the function at the first point to get us the incremental change in the function. Now, if we just move a little bit, we expect it to be very predictable how the function's changing. There should be no arbitrary jumps, and that's because we're under the impression that this function should be somewhat smooth, it should be well defined, it shouldn't jump sort of erratically around, it should be a nice smooth transition going up or down. But that's connected to this idea of differentiability, and that's what we're trying to capture. We're trying to capture the notion of differentiability. So if delta z is very predictable, the increment is very predictable, how this change happens in terms of the rates of change of f with respect to x and y, so it's partial derivatives, then we say the function's differentiable. What do I mean by if I think this delta z behaves predictably? It really means that if our surface is closely approximated or is approximated very well by the tangent plane. If the tangent plane at that point AB is a good approximation of the function, then this increment is quite predictable. I can figure out how much this change should be. How much should that change be? Well, it'll be what it takes to get back onto the tangent plane if I move a little bit in the x direction and a little bit in the y direction. Then this tells me how much it takes to get back onto the tangent plane, because that's essentially part of the equation of the tangent plane. But the tangent plane is just a close approximation to the surface itself when I'm at nearby points nearby AB. So there's an adjustment factor to get equality, to get back right onto the surface. And the thing here is that this adjustment factor involves these epsilon 1, epsilon 2's, these numbers, which get smaller and smaller as delta x and delta y go to 0. So this adjustment factor should shrink to 0 the closer I get to the point AB, or if I don't travel very far away from AB. I should be basically on the tangent plane. That's a good approximation. The further I move away from the point AB, the worse my tangent plane approximation is, so that's where these epsilon 1's, epsilon 2's sort of come up and make up the difference. So the bottom line here is that if the tangent plane is a good approximation to the function at that point, then an expression like this holds, that delta z should be approximately the tangent plane plus some adjustment factors. And if an expression like this holds, we say that it's differentiable. So this is a technical way of writing the idea that the tangent plane is a good approximation. And the reason we need a technical way is so that we can prove results. I can't just say, well, if the tangent line is a good approximation, because I don't really know what good is in some definitive sense, then I couldn't prove a result like the next theorem. But however, with this technical definition, which is just capturing the idea that the tangent plane is a good approximation, then we can prove the next theorem, and this is the theorem that we're going to use to be able to show functions are differentiable. So the theorem says that a function is differentiable if its partial derivatives exist, and you might think, well, that's a gimme. The partial derivatives should exist for it to be differentiable. So the partial derivatives exist near the point you're interested in, but we also have one extra condition. They have to be continuous as well. Just the existence of the partial derivatives alone is not enough to guarantee differentiability, unlike in Calculus 1, where just knowing that a derivative exists was enough to tell you that it's differentiable. In Calculus 2, knowing that the partial derivatives exist, these two partial derivatives, is not enough to guarantee differentiability. However, this theorem tells us that if they are also continuous, then that is enough. So it's a very, subtle point, but we'll look at an example that illustrates this. So first, the warning. So the warning is, it's more or less the warning is the very last bullet point. So maybe I won't say warning just yet, but I'll say, in summary, what this definition and this theorem is really telling us is that a function of two variables is differentiable if it can be closely approximated by a linear function, or if the tangent plane is a good approximation to the surface at that point. That's really what we're capturing with this idea of differentiable. And then that gave rise to the technical definition, which can be used to prove the theorem. And so from the theorem, we have that it implies that partial derivatives of a function f are continuous. Then the function is differentiable. So that's enough to guarantee differentiability, existence of partials, and they're also continuous. And on the other hand, if a function is differentiable, then its partial derivatives exist. But the warning is that last bullet point. Just knowing the partial derivatives exist is not enough to guarantee differentiability. So there are functions where you can construct the x partial derivative, the y partial derivative, they both exist at a point, they both turn out to be some values. The problem is that when you use those to construct the tangent plane is not a good approximation of the entire surface near that point. Let's see an example of this. So here's a surface. You can see the equation over here. This is the surface that gives, or the function that gives that surface, 2 times x times y times x plus y over x squared plus y squared. What I've done is I've constructed the tangent plane. Now how have I done that? Well, I've just taken the x partial derivative and the y partial derivative of this function at 0, 0. It turns out both partial derivatives are 0. So the tangent, and you can kind of see that from the diagram, you actually don't even need to compute this. So if I look at the y-axis, is this axis going straight up the page now? And if I look at how the y-axis intersects our surface, or I should say the plane made up by the y-axis and the z-axis, so the yz plane, it intersects our surface in a horizontal line. In fact, it intersects right along the y-axis, and that line has slope 0, so the y partial derivative is 0. You can also see that the x partial derivative is 0 by looking at the intersection of the xz plane and the axes. The x-axis is this one that's coming right out of the page at us. I'll zoom out a little bit so you can see a little bit more. So now you can see the x-axis and the x partial derivative is 0. So x partial derivative is 0, y partial derivative is 0, so we can construct the plane, which is going to be the tangent plane. However, the tangent plane is not a good approximation of the function at the point 0, 0. Why can I say that? Well, if it's a good approximation, it means the further I zoom in and zoom in and zoom in, the more closely the surface is going to look like that plane. However, in this particular case, there are some directions which will never flatten out. And so I've indicated one here. I'll just turn it on. It's what I call this ridge line. So this is a line that lives on the entire surface, all the way down. So it's right on the surface. And so as I zoom in and zoom in and zoom in on the origin, this ridge line is always there. It doesn't flatten out the closer I zoom in. So for points along this line, this red line, they're not closely approximated by the tangent plane. They don't flatten out there. They're just a straight line that passes right through the origin. So this red line is never closely approximated by the blue plane. And therefore, this surface is not approximated very well by the tangent plane at the point 0, 0. And therefore, it's not differentiable, using this sort of informal idea of differentiability. So why is it not differentiable in this case? Well, it turns out that the partial derivatives, even though they exist, the partial derivatives are not continuous at the origin. And so it's not enough to be that the partial derivatives exist, because in this case the partial derivatives exist, but the tangent plane isn't a good approximation. So that's an example of this warning, this last little bit, having both partial derivatives at a point, which that example did, does not guarantee differentiability. All right, so what can we do with this? Well, we can use the theorem to show that a given function is differentiable at a point. And so we'll do that now. We'll see how we can apply that theorem. So explain why this function is differentiable at the point 3, 0. Again, what it means to be differentiable, if you're thinking, what does it mean to be differentiable? It means that the tangent plane is a good approximation to the function at the point. Or the linearization is a good approximation to the function near the point. That's what it means to be differentiable. It means that it roughly, if you zoom in far enough, it looks like a linear object. That's the same kind of idea in Calculus 1. It's differentiable at a point if you zoom in far enough and it looks like a line, the tangent line. Okay, so let's explain why this function is differentiable. Why is it differentiable? Well, one way we can do that is we can just check the x and y partials and see if they exist and are continuous at the point. So if I look at the x partial derivative, this is going to be, well, maybe I'll write down the function first in a way that's going to be helpful to taking its derivative. I'll write it down as a power. So then when I do the x partial derivative, it's 1 over 2 times the square root of the inside times the derivative of the inside, which is 1. And the y partial derivative is the same thing, 1 over 2 root x plus e to the 4y times the derivative of the inside. Derivative of the inside is the derivative of e to the 4y, so that would be 4e to the 4y. So there's our two partial derivatives. So do they exist at the point 3, 0? Yep, they exist at 3, 0, because I can plug 3, 0 into both of those expressions. There's no division by 0 happening there. You can work those values out. And both of these are continuous at 3, 0. Why are they continuous at 3, 0? Again, there's not a problem with division by 0. So the function x, the function e to the 4y, those are both continuous at 3, 0. The sum is continuous, the square root is continuous, multiplying by 2 is continuous, taking the reciprocal is continuous only when the function doesn't vanish. And in this case, at 3, 0, the function, or the thing under the square root sign, isn't vanishing. So these are continuous. Both of these partial derivatives are continuous. They exist. And therefore, f is differentiable. This is by that theorem. It's differentiable at 3, 0. So what good does that tell us? Well, that tells us, since it's differentiable, that tells us that the linearization is a good approximation to the function. So the next part of the question says, find the linearization. Okay, we'll do that. We'll find the linearization. L of xy is equal to f of 3, 0 plus the x derivative at 3, 0 times x minus 3 plus the y derivative at 3, 0 times y minus 0. f at 3, 0 is the square root of 3 plus 1, square root of 4, or 2. F sub x at 3, 0 is 1 over 2 times the square root of 3 plus 1, square root of 4, 2, so that's 1/4 x minus 3. And then fy of 3, 0. So when I plug 3, 0 in, I get 4 over 4, which is 1, and so that just becomes a y. So there's our linearization. And since that's our linearization, what we want to do is we want to use it to approximate f of 3.1, negative 0.1. And so that is approximately given by the value of the linearization at that point. We can plug that into our linearization. It's 1/4, 3.1 minus 3, so that's 0.1, plus plus y, which is negative 0.1. And so then we can just work out what the value of this is, and this is 1.925. So that's just a little bit of basic arithmetic we can work out, no problem. And the idea is that we are able to work out an approximate value for this function at 3.1, negative 0.1, by using a nearby point, 3, 0, which we could work out the exact value of the function, and using the derivatives, the partial derivatives, to tell us how much the function had to change by when I moved to the new point. The arithmetic was a lot simpler to do, getting the linear approximation, than it would have been to actually work out the original function at 3.1 and negative 0.1. If I was to plug 3.1 and negative 0.1 in, I'd have to plug 3.1 plus e to the 4 times negative 0.1. So then I'd have to work out those, probably using a computer or a calculator. But the calculations we didn't require the use of calculator. It was just a very basic amount of arithmetic in the end, which wasn't so difficult because this is just one decimal place, and so quite straightforward to work out. So it was a lot easier to do the calculation to get the approximate value. And this is sort of the moral of the story, is that when you do computations, sometimes computations can get pretty complex, pretty detailed, and it might be easier to just do them with linear objects and be content with an approximation. And this is the kind of thing that happens when you move forward in your math and engineering and physics classes, is getting approximations is in some sets quite a lot easier than working with the actual values. So having techniques for doing approximation end up being essential. And this is one type of technique, this idea of linear approximation. All right, and that leads us now into the differential. So what is the differential? I'm just going to scroll back to the linearization. Here's our linearization. I'll get rid of a few of these markings here. So remember, the linearization said you've got a function, you've got a point you're interested in, a, b, and you'd like to work out a linear function that's a good approximation of this function. So how do you work out that linear function? Well, you take the value of the function at the point you're at, and then you figure out, if you move a little bit away, how much your function is going to change by. And this amount that it changes by is what we're going to call the differential. So our linearization is essentially the point you're at plus the differential. That's what we're calling the differential. So we'll scroll back down here, and we'll see that that's precisely what the definition is here. The differential was precisely that part of the linearization. And those are just three different ways to write it using various notations. So delta x notation or dx notation for change in x, same with delta y or dy, those are interchangeable. You can use the subscript notation for partial derivatives, or Leibniz notation, which is the dz by dx or dz by dy, however you want to use it. That's the differential. So let's work out an example. Here we've got a function f, and we want to find its differential. So the differential for the function is going to be given by the x partial times dx plus the y partial times dy. The x partial is the derivative of sine of x, so that's going to be cos of x dx. The y partial is the derivative of 3 cos y, that's negative 3 sine y dy, and there's our differential. That's our differential dz. Again, the key idea here was this differential is basically approximating the increment. This is if I'm standing at a point and I move a little bit away, change my x value by dx, change my y value by dy, how much do I have to go up by to get back onto the tangent plane? That's this value here. How much do I have to go back to get onto the surface? That's delta z. And these things are closely approximate to each other. So this dz, the differential, is a good approximation to the increment. And so how do we use that? We can use it in an idea like this. So we've got our function. We can calculate f of pi by 2 and 0. That's a straightforward value to calculate. That's sine of pi by 2. That's 3 times cos of 0. Sine of pi by 2 is 1. Cos of 0 is 1. So this has a value of 5. So that's a straightforward value to calculate. And now it's saying, now calculate the value f of 29 pi by 60 and pi by 50. And your first reaction should be 29 pi by 60, that's close to pi by 2. Pi by 50, that's a pretty small number, close to 0. So f of this value should be close to 5. And the question is, how close to 5? How close to 5 is it? How do we do it with a linearization? We notice that L, well, maybe I'll say it this way. F of 29 pi by 60 and pi by 50 is approximately given by L of 29 pi by 60, pi by 50. And that linear approximation, we can use the linear approximation at the point we know all the information at. That's pi by 2 and 0. So I'm going to take this linear approximation, which was constructed at pi by 2 and 0. So that would have been f of pi by 2 and 0 plus f sub x at pi by 2 and 0, x minus pi by 2, plus f sub y at pi by 2 and 0 times y minus 0. So that's our linear approximation. And this right here, well, maybe I should get the plus as well. This right here, that's our differential. So when it says calculate f of pi by 2 and 0, that we've done right here, that's 5. And then the differential, which we still need to do, and use that to approximate this value. Well, through linearization, it just says take the value of the function at pi by 2 and 0 and add the differential, and that's going to be the approximate value of the point you're interested in. So let's work out the differential. What is our differential? In this case, we want the differential at the point pi by 2 and 0. So that's at pi by 2 and 0. And so I'm going to look at the top of the page at my differential. When I plug pi by 2 and 0 in, that's 2 times cos of pi by 2, that's 0, dx, plus sine of 0 is 0 dy. So the value of our differential is 0. So we've just worked that out. That's now 0. And so what this means is that f of 29 pi by 60 pi by 50 is approximately given by the linearization, and this is 5 plus 0, or 5. So what this says is that 5 was the value of f of pi by 2 and 0, and because both partial derivatives were 0 at that point, it means our function, our surface is flat there. So if I move a little bit away from the point, pi by 2 and 0, to this new point, 29 pi by 60 and pi by 50, so I've basically gone, changed my x value by negative pi by 60 and changed my y value by pi by 50. If I move that little bit, then my z value doesn't change at all because I'm on a horizontal tangent plane. And so since my z value doesn't change at all, that's my differential dz. It's not changing. It means that that approximation for that new point is really just the value at the other point. So 5 is a good approximation of that point. So that's how we can use our differentials as a part of linear approximation. It's really just one component of the approximation. It's the change in. So it's the value of the point you're at is the function value plus the change in is the differential part. Now here's another example of a differential and how they're used, and this is probably how you will most often see differentials being used, and it's the idea of errors. So here we've got a closed rectangular box and we're trying to figure out what is the volume of it. Now how do we figure out the volume? Well, one way is to just measure the side lengths of the box. So I'll measure a side x, measure that side y, measure that side z, and then I can compute the volume by just multiplying those three lengths together. The problem is, when I do my measurement, I'll measure one side to be 80, the next side to be 60, the next side to be 50. I'll take my product of those three values, get my calculated volume, but my calculated volume may not be correct because there's errors in the original numbers I used when I measured the sides. So this could be just reading the tape measure, right? I can sort of only estimate where I'm reading on the tape measure up to a certain value, and I could be off by 0.2 of a centimeter. And so how do those reading errors, or how do those measuring errors factor into the calculated error of the volume? So that's this question. If you use these values, 80, 60, 50, but you know that there's errors in those values, each one of them could be off by up to 0.2 of a centimeter, what is going to be the maximum error that you could get in your calculated volume? So the maximum error we're going to get is, essentially we're interested in what's the differential, the dV. So we want to know maybe I'll write it down. We want to know the magnitude of dV. Now, how is it that I wanted to know that? Well, think about what dV is. dV is the differential for the volume, or in other words, it's the change in the volume given the changes in the inputs. So I'd like to think about it input-output. So if our inputs, x, y, and z, change by about 0.2 of a centimeter at most, if the value I used for x changed by 0.2 of a centimeter, because that's the possible error I had in the measurement, and my change in y was 0.2 of a centimeter, and my change in z was 0.2 of a centimeter, what is my change in volume, my calculated volume? How could it possibly be changed? And I want to know the maximum value of that. So what we have is, we have that the differential, dV, is given by the derivative with respect to x times dx plus the derivative with respect to y times dy. This is a function of three variables. So far we've just studied two variables, but the same pattern holds for three variables, and that's what we have up here as well. It's just saying that when you're working out a differential, it's just take each variable and do the same thing. So this would be the variable, the derivative of v with respect to z times the change in z. So that's the differential, dv. That's how v will change if the inputs x, y, and z change by dx, dy, and dz. We're interested in the magnitude of this, so I'm interested in the magnitude of these, and that's less than or equal to, well, actually I'll do the less than or equal to after, because we can work out what Vx is. Vx is the derivative of v with respect to x, that's yz dx, plus the derivative of v with respect to y, that's xz dy, plus the derivative of v with respect to z, that's xy dz. Now that's at most, I've got the absolute value of the sum of three things. I can work out their individual absolute values and add them up, and that will be an upper bound on the absolute value of the sum. I also know that the variables x, y, and z are all positive because they're measured lengths. So I can bring my absolute values down in this way inside and apply them directly on these errors. Okay, so that's our upper bound for the change in the volume. And now what we want to do is we want to take particular data points. So we've got for x equals 80, y equals 60, z equals 50, dx at most 0.2, dy in magnitude at most 0.2, and dz in magnitude at most 0.2. Why is that? Well, that's our error. We're told that there's an error of 0.2 of a centimeter in each dimension. So that means when I measured 80 centimeters, I'm off by plus or minus 0.2 of a centimeter. So my change in x could be anywhere from negative 0.2 of a centimeter to positive 0.2 of a centimeter. So the absolute value of dz is less than or equal to 0.2 of a centimeter. And so using those values, we get that dv is at most, so it's 60 times 50 times 0.2 plus 80 times 50 times 0.2 plus 80 times 60 times 0.2. And if we work out those values, we get 2,360 cubic centimeters. And so what is that telling us? That's telling us that if we've measured our side lengths to be 80, 60, and 50, and due to the instrument we use, we know that there's a possible error in each of those numbers of 0.2 of a centimeter. And so I use those numbers to calculate the volume. Then my volume is off by at most 2,360 cubic centimeters. And depending on how you look at it, that could be a significant value. It could be a significant amount you're off by, and so you may want to remeasure using more delicate instruments that have smaller errors, or maybe this is a fine error. Maybe you're not too worried that you're off by at most 2,400 cubic centimeters. All right, so that's it for this section. Thanks very much for watching.